Hi everyone, I hope you're okay, and I really hope that the videos will keep uploading and helping you out. This is the 11th and last video, guys, whereby I'll be tackling past exam questions on Doppler effect. Yes, there are other 10 questions before this one, and it's very important, guys, for you to know how to answer these types of questions because it will give you an edge in an exam. So please do share the video to your peers. I believe that the video will also help them as well. Yeah, let's just get right into it. We are told that a car moves at a constant velocity of 22 meters on a straight horizontal road towards a stationary device which can both emit and detect sound waves. The device the device emits sound waves with a frequency of 24,000 hertz. These sound waves are reflected off the car and reflected sound waves are then detected by the device as well, as shown in the diagram below. So these sound waves will produce a frequency of sound, and then the car will detect that frequency, and then the car will in turn produce that frequency, and then the device will detect or rather the device will observe the reflected frequency. Okay, let's answer the questions. Firstly, they want us to state Doppler effect in words. Doppler effect is the apparent change in the observed frequency of the source as a result of relative motion between the source and the observer. Doppler effect is the apparent change in the observed frequency of the source as a result of relative motion between the source and the observer. Okay, now we are told that if the speed of sound in air is 340, calculate the reflected sound waves detected by the device. Okay, firstly, guys, we are moving from A to B, right? From A to B, what happens? The device emits sound waves, and the car, and then the car will detect the sound waves. Are you together? At the same time, for C to D, what happens is that the car will then reflect the sound waves detected back to the device. Are you together? So the sound starts from the device, goes to the car, and then the car reflects the sound waves and then the car reflects the sound waves back to the device. Are you together? So for us to find the frequency that the device will detect, the reflected frequency, we must first find the frequency that will be observed by the car. We'll simply say that means we're focusing on path A to B of our sound waves. Are you together? For path A to B, we don't know the frequency detected, but I know that the source is simply 24,000 hertz, and then the velocity of the source is stationary, but the car is moving at 22 meters per second. The speed of sound in air is simply 340 meters per second. Are you together? By just using this information, we can calculate the frequency detected by the car. I'll simply say FL is equals to V plus or minus VL all over V plus or minus VS times FS, right? We're dealing with FL. My denominator will only have speed of sound. Why? Because the velocity of the source, my source, which is the device, is stationary. So I'll only have V there at the denominator. On my numerator, I will have V and also OVL multiplied by Fs. But now, guys, I know that my listener is moving towards the stationary source, which is the device. So since the listener is moving towards the stationary source, that means I have a plus over there. So I'll simply have 340 plus 22 all over 340, all multiplied by 24,000. That's 340 plus 22 divided by 340, all multiplied by 24,000. This will give me 25,552.94118 hertz. So basically the car will detect this amount of frequency. Are you together? And then the car will reflect that frequency back to the device. So now our car is our source. Whenever we talk about the reflected frequency, the car will become the source. Since the device has to detect the reflected frequency, the device will become the listener, or the device will become the observer. So I now know that for C to D, that's when I'm talking about the reflected frequency. The frequency of the listener, that's what I'm looking at. That's what I'm looking for. And the frequency of my source, that's simply 25,552,94118 hertz. And then the velocity of the listener. Remember that, guys, the device is the listener now. Whenever we talk about the reflected frequency, so our device is the one which is stationary, and then but the source is our car now, because the car is the one which is reflecting the frequency back to the device. Our car is moving at 22 meters per second. The speed of sound does not change. We still have 340 meters per second. Okay, now they want us to find the frequency, the reflected frequency detected by the device. Simply say FL is equals to V plus minus VL all over V plus minus VS times FS. Right now, guys, our listener is the one which is stationary, and hence our numerator will simply have the speed of sound only, because the velocity of the listener is 0. At the denominator, we'll have the speed of sound as well as the velocity of the source, which is the car, times the frequency of the source. The only difference over here is that, guys, okay, not the difference, rather, since the source is moving towards the stationary listener, it simply means I'll have a minus there at the bottom. So I just have to substitute. FL is equals to 340 all over 340 minus 22, obviously multiplied by 25,552.94118. And then I'll get the value that I want. I'll simply have 340 all over 340 minus 22 multiplied by 25,552.94118. This will give me 27,320.76 hertz. So the device will detect the reflected frequency of 27,320.76 hertz. That's how, guys, we're supposed to tackle that question over there. That's 27,320.76 hertz. Okay, and then now we are told that the spectral lines observed for a distant star show that the star is moving away from the Earth, explain why by referring to frequency, how one can deduce that the star is moving away from the Earth. When the star is moving away from the Earth, guys, it will simply mean that the star has been redshifted. Are you together? Red has the lowest frequency in the spectrum. So since red has a lower frequency, it simply means the star will have a greater wavelength. Are you together? So since it has a greater wavelength than the lower frequency, it simply means the star is actually moving away from the Earth, or the universe is simply expanding. That's how, guys, you're supposed to tackle that question over there. Just stay tuned, guys, and I hope that the video helped you out. And please don't forget to subscribe and obviously share. Bye.